Uh, we still talking about casting. We stopped here last time. Uh, we talk about shrinkage. Today we're going to talk about shrinkage and shrinkage. يعني بالعربي يعني الانكماش يعني وده بيحصل نتيجة ان يعني this happened due to you heating, you melting the material in a liquid form, and you pouring material in a mold, and then material have to solidify. So when material solidify, meaning situation change from liquid to solid, density will increase and volume will decrease. Volume will decrease, meaning shrinkage will happen. So this is usually happen. So you can see that this is a cooling. So shrinkage in a liquid, and then solidification, shrinkage, and shrinkage in a solid. So this is a shrinkage. This is a volume actually. This is a density. Sorry, density increase. This is the time. When the time increase, with the time increase, density will increase also. So when you get higher density, it is a liquid form, low density, and then density will increase. Density will increase. When density increase, actually what happened? Volume decrease, which is a shrinkage. So shrinkage usually happen associated with casting process. So when shrinkage happen, dimension change. So let me just explain to you more about this. This is a liquid. You put a liquid here. This is a mold, and this is a liquid. You put the liquid in the mold. When you put the liquid in the mold, what happened? Initially, the outer layer starts solidify. This is the outer layer which is in contact with the mold. Because the highest heat transfer rate will be here. Then this is the highest heat transfer rate will be here in this area, which is in contact with the mold. Then immediately this part will solidify, outer surface will solidify. The core one is still liquid. The core one is still liquid. And liquid need to solidify, then another layer and another layer and another layer. Many layer will solidify. You can see that. More solidification will happen. Still the core is liquid. Some area still inside. And finally, when all parts solidify, probably get void here. Because why get void? Because this part already becomes solid, and here maybe there are still remaining liquid. When this liquid solidify, you need to shrink, but the outer fiber not allowing, because already solidified, already become solid, not allowing. Probably then it could happen like cavity happen inside. This cavity is like defect will not accepted. So it is not accepted actually in a casting. This defect must be avoided. The question is how to avoid such defect in the cavity in the casting. That's what we're going to discuss here in this class today. So anyway, shrinkage happen. When shrinkage happen, actually dimension also change. You can see start here, but the end with here. Dimension, you start, it is totally filled here. Then you see dimension actually is changed, and the part become a bit smaller. Then there are a shrinkage and there are a void. So there are a shrinkage mean dimension change, become smaller, and there are a probability of void could happen in a casting. We need also to solve this problem. One by one, we discuss first about shrinkage. Shrinkage, we have whatever we call linear shrinkage and volumetric shrinkage. Linear means the line, every line in the part will shrink. Volumetric means the total volume will shrink also together. And luckily, this kind of linear shrink and volumetric shrink, we know. Someone will ask me how we know that. We just do experimental work. They usually do experimental work in a lab to know what is the linear shrink and what is the volumetric shrink for different material. Then you can see that for different material, this is aluminium, this is brass, this is cast iron, and so on. For different material, shrinkage, the linear shrinkage and volumetric shrinkage can be identified in the table, in the machinery handbook, in the table. You can find this kind of values. So luckily we know it, so we can consider that while we preparing the mold, we can consider extra volume. While we preparing the mold, we can consider extra volume to accommodate this kind of linear and volumetric shrinkage. Linear and volumetric shrinkage, both. Let's take an example, a rectangular plate, this one rectangular plate. We would like to cast this one. It's very simple. Rectangular plate need to cast it by open mold. This is the open mold meaning like this one. So this is the open mold. A final dimension of the plate, final dimension of the plate, it means that after shrinkage, this is what we need to have. Actually, this is what we need to have at the end of the casting process. So the final dimension is 180, 220, 23 millimeter. What is the volume here that was poured in the mold? What is the volume? What is the volume of the aluminium that was poured in the open? يعني عايزين بالعربي عايزين نعرف الفوليوم بتاع الالومنيوم اللي عشان finally you have this one. معلش هي الرسمه مختلفه شويه يعني، لكن يعني ده البليت، يعني البليت عايزين نعمله، بس هنا انا بوريك بس الاوبن مولد يعني just I would like to show you what is the open mold يعني. This is the idea. So the question is, what is the volume of the aluminium that you need to pour in the mold to finally get this dimension? Definitely volume will be bigger than the volume of the final. This is the volume. Volume will be different because when you put liquid, volume will be bigger. When you have shrinkage, volume will getting smaller, density increase. He said that linear shrinkage is known 1.3% and volumetric shrinkage is also known, which is 6%. When you come to the linear shrinkage, one by one, then linear shrinkage, every line will change. The dimension of every line will change with the linear shrinkage because every line will shrink also as well. So linear shrinkage 1.3 will consider for every line for 180, for 220, and for 23. So 180 divided by 0.987, which is 1 minus 1.3% or 0.013 or 0.013. 0.013 is then you get the balance here. So 180 divided by 1 minus linear shrinkage. Second one is 220. Also, we will consider the linear shrinkage. So linear shrinkage will be considered here for 180. Linear shrinkage will be considered here also in 220. Linear shrinkage will be considered also here in 23. Then if you multiply the new dimension, this one will not become 180, become bigger than, will be bigger than 180. This one will be bigger than 220. This one will be bigger than 23. Then you multiply, get the volume. This is a volume considering the linear shrinkage. Also, the volume itself will contract or will shrink. Then we have 6% volumetric shrinkage. This is a volumetric shrinkage. So we have 6% volumetric shrinkage. So this 6% volumetric shrinkage, we're going to consider a volume. So this is a volume actually. This is a volume. This is a volume we're considering linear shrinkage. And then we bring this volume here. This volume will also change considering the volumetric shrinkage, which is 1 minus 0.6. 1 minus 0.6. Then volume will change, then we get bigger volume. So actually, finally, this is a volume that we need. This is a volume of metal or volume of aluminium that we need to use to pour in the mold. Finally, get this one. This is a volume of the liquid. This is a volume of the liquid that we need to have. Then we need to pour here in the open mold. So this is the one. This is the one. This is the volume we need to put in an open mold. Then finally, you get this dimension, which is this one. That's it. So this is about how to consider the linear shrinkage and volumetric shrinkage. And more details will come in the next chapter about how to consider many allowance like shrinkage allowance, and we will consider this in the next chapter in details actually about the shrinkage and the machining allowance and draft allowance and so on. Right. Next question is about the void happening here. I told you that when shrink happens, the outer fiber will solidify earlier and later the core will solidify, and probably maybe you get void here because this liquid which is still remaining in a core, not solidified yet, while outer fiber solidified, This one would like to solidify, this would like to shrink, but no way, because the outer fiber already solidified. Then probably here you get void or you get cavity, which is not acceptable. So the question is how we can avoid, what we can do to avoid having such a defect. Because if you have a defect like this in a cast, this one considered as defect mean rejected, mean scrap. So we would like to avoid having this one. We call it directional solidification. We can apply what we call is directional solidification. So what is a directional solidification? Actually, if I ask you how to solve the big problem here, the big problem, why is this happen? The big problem is outer fiber solidify first, liquid in the middle solidify later. Then you get this cavity. You agree with me? Then the question is how to solve. Solve actually, if you can, if I'm just say if you can change the solidification direction instead of from outside to inside, then make it from inside to outside. Mean core solidify earlier and later the outer fiber solidify. Then core will become solid, the outer fiber will be liquid, liquid solidify later, then shrink, then no problem, then you avoid having this one. Do you agree with me? So probably this could be the solution to change the direction of solidification. Instead of solid from outer fiber to inner fiber, make it from inner fiber to outer fiber. So how we can do this? The question how we can do this? Actually, by whatever we call directional solidification, we adding external shell in the places that we know this void could happen, like here. You will ask me how you know that the void will happen here. Actually, we have what we call is a hotspot. Hotspot happen when the dimension actually change. You can see that this is a dimension. This is a dimension. You see that dimension is okay. This is a dimension. So this is a dimension. You can see that this is the dimension here. Cannot do it anyway. So this is the dimension. But when you come to here, in this area, you see that what happened? Dimension getting bigger. So here the dimension is again getting smaller. Dimension again getting smaller. So you can realize that when dimension is small, and here small, and here suddenly in this area dimension getting big, then you can realize that outer fiber will solidify earlier. You definitely, for example, I'm just telling an example, definitely will get void here in this area because you suddenly get bigger dimension. Right? So now we have a problem here. We understand that even before we do casting, we can realize that here, because we have sudden bigger dimension in this area, then high probability to get cavity here or good void here or whatever. We need to avoid, if you get this one, you get defect. So how to do? How to solve the problem? Actually, they added whatever we call external shell. External shell, it means that we added extra material here and we added extra material here. So this one we call is shell here. We added extra material here and we added extra material here. So this is the whatever we call it external shell. So what will happen if you added external shell? Will happen? Actually, this external shell is very important because it's like heat sink. Heat sink means absorbing heat. Based on a Cheverny law, the solidification time, because we need here to reduce, actually the issue is we need to reduce the solidification to make it faster. Solidify inside, liquid here, solidify quickly, more quickly, faster than the outer fiber. Then We would like solidification start from inner to outer, not from outer to inner. If from outer, if you just leave it from outer to inner, then you get void. We would like the heat, absorb heat quickly from inner, quickly, so solidify early. Then we need to solidify the part in the inner surface before outer, then avoid having this one. We put a heat sink here. This is the heat sink, or we call it is the external chill. Then this one will absorb heat quickly. This will absorb heat quickly from here. Absorb heat. It's like heat sink. So absorb heat. So this kind of external shell will absorb heat quickly. Absorb heat quickly from this area. Allow this one solidify earlier or quickly. Then become solid. Then okay, finish. And then other liquid, then liquid solidify later. Then no issue will happen, right? The question is, what is the fundamental? Fundamental is a Cheverny law. Cheverny law says that the solidification time equal to constant multiplied volume divided by surface area squared. If you increase the surface area, the time will reduce. Exactly that's what we're happening. We're increasing, make it bigger surface area here. When you increase the surface area, which is in contact with the mold, it means that the time needed for solidification is getting less. So higher volume is same, almost same, but surface area is getting higher. Then when you added the higher surface area, then you get what we call is, this is actually here. When you look to this one in 3D, then you can see here, this one is a shell, external shell. Right, did you get it? So this is external shell. So this is here is the external shell. Right. So you can see that this external shell absorb heat, you increasing surface area, so surface area in contact will be higher. So surface area is higher here, meaning that absorb heat quickly here. So that we call it heat sink. Absorb heat quickly to solidify this part quickly. Then you can see, can solve the problem, well, you can solve it. Someone will ask me, this is extra material, but we don't want, actually, finally, we would like to have this shape, not this one. So now you added extra material here. So the part becomes something different. What to do with that? Actually, you remove by machining. By machining, mean after casting, when casting finish, then you take this part to the machining, and then you cut this area, and you cut this area, then finally you bring back the dimension to the desired shape or the original shape. You told me that, but this is waste of material. You cutting this one, and this is waste of material, unavoidable. Then this is unavoidable, and must have external shell. If you don't have external shell, then you get defect. If you don't have external shell, then you get defect here. So now you have the choice to totally waste the cast and then become scrap, or you added this kind of extra material and remove later by machining. Definitely it's better to add this extra material and remove later by machining. It will help you to get a good cast part and avoiding having defect in here, as you can see, right? Is it clear? This is what we call is external shell. We need to add it in the design early when we detect that, when we understand or when we realize that we having or we may having a defect in a part. Several design, you can see that if you would like to have this one in this way, then you get defect because you get bigger dimension. Then you see here, this is the dimension, this is the dimension, you get bigger, sudden bigger dimension here, then you get defect. Then you added shell here. You added external shell here, then absorb heat in this side, then avoid having this one. Also here, if you're producing something like this, definitely you will get defect here, then adding external shell here and here to absorb heat. And if you designing something like this, get defect here, definitely you will get defect. You see, this is a bigger dimension, very big dimension. We call it hotspot actually. We call it a hotspot, then you will get big defect here. Then you added this kind of external shell everywhere. If you have this one, the blue one, then definitely you will get something like void here. Sorry. you will get void here in this area definitely. So how to solve? Then added shell. Added shell mean you added certain material, you put certain material in contact here to increase the surface area, so this one can absorb heat quickly from this part. Then simply you can avoid having the effect in this area. Yes, Mubarak, I'm listening.
Doctor, to avoid this cavity inside, how can I
Hmm.
determine the shape of shell and the place of the shell?
Um, yeah, the idea, Mubarak, the idea is to increase the surface area. You agree with me?
Yes.
Around this part, you need to increase the surface area. This is the issue. The question how to then added more material to increase the surface area. Where to put this one? This is your question. Where to put? To put it very close, as as close as you can to the defect area. Where is the defect area? Defect area here. Then you must put it here very close to the defect area, so it will be concentrated here and absorb heat exactly from this one. You cannot put here, for example, no effect. It must be close. You have to find where is the closest area, the nearest area from the defect. For example, here, where is the nearest area? Nearest area it could be here and here. Then you added here and here. Nearest area, right? So it's here. Then you put nearest area, the nearest possible area from the defect. You will ask me how to know the defect. You have to know, because when a dimension is getting bigger, suddenly getting bigger, somewhere then defect will happen. This is very logic. Actually, computer can detect that. Now there are software actually, but we explaining the fundamental to you. We have to explain why it happened, and when you find the computer do something, you have to know what is that and why computer creating this one. There are software now, we call it the Magma software. It is a casting software. Computer, when you put the design in a computer, computer can tell you must put here and here and here and here and here based on what? Based on this fundamental, right? That's it. So this is the answer. If you could, did you get it?
Yeah, it's clear now.
Yep, right. That's it. So this is about shrinkage. Next, we're going to talk about the bouncy force. Next, we're going to talk about the bouncy force. Okay, bouncy force. This is really very important. I hope you give me your attention. Please give me your attention. Actually, full attention. I need your full attention with about the bouncy force. Do you know what is a bouncy? When I told you what is a bouncy, bouncy mean طفو. In Arabic, bouncy force mean قوة الطفو. عارفين الطفو يعني ايه؟ مركب مثلا، بتحط مركب في المية. If this is a water, this is a water, right? You put the boat here. This is a ship or boat. You put in a sea or in the water. What will happen? It will float. This one will floating. This one will be floating here, right? Will be floated here. So this is a chip. It will be floated here. يعني هتطفو. يعني لو حطيت مركب في المية، المركب دي هتطفو. عندك ايه هنا? What is the forces applied here in the chip? Is the weight of the chip. This is the weight of the chip, and this is the bouncy force. So what is a bouncy force? Bouncy force is a liquid force. When you put in a liquid, this is a liquid force. The liquid force pushing this ship or boat up, pushing this one up. Then it will be float, right? You understand me? So انها هتطفو، يعني قوة الدفع من بيقولوا عليها دي قوة الطفو اللي هي ايه؟ اللي هي الباونسي فورس. يعني هي from يعني this one applied on in the part from below to up, pushing up, and weight is against the floating or the bouncy force, right? This is generally liquid force. Not only water, but this is generally liquid force. So liquid force always applied, usually applied whenever we have a liquid, then this force usually applied. Then in our case, which is a casting, when we come back to the casting, you put liquid inside, right? You agree with me? You put liquid inside to fill all the gap. When this one happen, the bouncy force will be applied because there are a liquid here. This is a liquid. This is the liquid to fill the cavity. So liquid here, this liquid, as long as you have liquid here, this liquid will apply bouncy force. Bouncy force to push this one cup, not the drag. Then now we have cup and drag. Then the bouncy force will apply, this is the bouncy force. Bouncy force will push, try to push the cup here up, to push it up. And the weight of the cup, this is the weight of the cup, which is this one. The weight of the cup is pushing down. So this is the weight of the cup pushing down, a bouncy force pushing up. What is the bouncy force? Liquid force. Liquid force. So liquid force pushing up. So what will happen if the bouncy, please listen to me carefully. Please listen to me carefully. If the bouncy force, this one, if the bouncy force or liquid force bigger than the weight of the cup, what will happen? This one will successfully push this one up and this one open. You will get open here. You get this defect actually. If the bouncy force is bigger, then this one will be open and you get spilled. The liquid will spill out. The liquid will be spilled out يعني يخرج بره البتاع ده. Then you get this kind of defect. Can you see that this is happened due to the bouncy force? Bouncy force was bigger, and the mold open and liquid will move out. When liquid moved out, then this kind of effect happened. So in case of bouncy force bigger, you get this defect. So what about if the weight of the cup bigger? If the weight of the cup bigger, there are no issue. If the weight of the cup bigger, there are no issue. If the bouncy force bigger, then there are an issue. Then you get this defect. So what we can do with that? If the bouncy force bigger, what we can do? We can clamp here. We can apply clamping here. We can apply clamping here. We can do clamping here and also clamping here. Clamping mean we put clamping force. We can apply clamping force here and clamping force here. Then we can avoid having this kind of defect. Is it clear? Is it clear, guys? Can you understand what I said?
Yes.
Yeah, okay. Then talk about the clamping force. Clamping force happen only, or we need to have clamping force only in case, only in case bouncy force bigger than weight of the cup. Then clamping force equal to what? Equal to bouncy force minus weight of the cup. Clamping force equal to bouncy force minus weight of the cup. Because if bouncy force bigger, if it is negative, mean weight of the cup bigger, then no need. Then clamping force 0 if the weight of the cup bigger. If this one negative, if this value negative, meaning weight of the cup bigger, then the clamping force is 0. Right. Then we need to calculate. So now we understand that we need to calculate what is a clamping force, or we need to calculate the weight of the cup. We need to calculate the weight of the cup. This is the weight of the cup. We need to calculate the weight of the cup. We need to calculate the bouncy force of the metal. Right? We need to calculate this one and see which one bigger. We need to calculate the bouncy force and weight of the cup and see which one bigger. If weight of the cup bigger, then okay, this one is fine. But if the bouncy force is bigger, then we need to take action and we need to do clamping here in the system, right? Then one by one, we need to calculate the bouncy force. This is the bouncy force. Bouncy force equal to calculate the bouncy force, which is the liquid force, equal to, please listen to me carefully, area at the parting line multiplied by the pressure at the parting line. Area at the parting line. Where is the area at the parting line? This is a liquid, right? This is a liquid. This is a parting line. Let me highlight. This is a parting line. It is a parting line. This is a parting line, guys, right? This is a parting line. This is a parting line. Okay? Then it is area, liquid, definitely liquid. We said this is bouncy force is a liquid force. So this is a liquid area at the parting line. Where is the liquid? Liquid is here. So the liquid, for example, cylindrical shape. If the cavity here is like this is a bar that you would like to produce. This is a cavity, for example, if this is a cavity here, then this is the liquid, right? It is totally filled. So where is the area as a parting line? The area as a parting line is this one. So this is the area actually. The area at the parting line. So we said that a bouncy force or liquid force equal to liquid area at the parting line. This is the liquid area at the parting line, which is a this is the area which is a rectangular area. This is the rectangular area. So this is the area at the parting line, which is area A at the parting line, multiplied by the pressure also at the parting line. The pressure at the parting line, pressure here as a parting line at this line also equal to, this is the pressure as a parting line equal to the weight density multiplied by the height. Weight density, which is gamma h. Weight density is liquid weight density. We still talking about it. When you said bouncy force, it is mainly related to the liquid. So liquid weight density, which is the gamma multiplied by h. H is the height of the liquid. This is the height of the liquid. So this is the height of the liquid. The height of the liquid, this one, applying the pressure here at the parting line. So it is gamma h. Gamma meaning rho g. Gamma means weight density, which is rho g, rho metal, liquid metal. This is the density of liquid metal multiplied by gravity acceleration multiplied by the h. And h here is the height of the liquid in the spiral. Height of the liquid in the spiral. To just explain this one, when you go to the pool, swimming pool, حمام السباحة يعني, we try to go to the water and then you go down. Whenever you go more down, whenever you go down and down and down and increase, the depths, you feel more pressure. Why you feel more pressure? Because the head of the line or the head of the water above you is become bigger. So the head of the liquid usually applying pressure. So this is a pressure mainly due to the head of the liquid above this line. So the head of the liquid above this line, which is the liquid in the spiral, this is the head of the liquid that applying pressure here at the parting line. So it is gamma h or rho g h. Rho of the metal, g gravity acceleration, h the head of the liquid in the spiral or above the parting line. This is the pressure. This is the pressure at the parting line. And area, then the bound force equal to the area multiplied by the pressure. This is the pressure at the parting line. This pressure at the parting line multiplied by area, which is this one. This is the area, rectangular area. Then you get the bouncy force. So this is the bouncy force. This is the way how to calculate the bouncy force. Next is weight of the cup. We need to calculate the weight of the cup. The cup here mainly sand, made of sand and flask. Can you see that? Flask, which is a metal container here. So flask here and sand. Actually, this flask usually not considered. We usually remove, or even if there, then the weight of the flask usually it's very thin. The weight of the flask usually ignored. We usually ignore weight of the. So actually, the weight of the cup. This is the weight of the cup. Actually, if we ignore the flask, this actually is the weight of the cup. Weight of the cup. If we ignore flask, if you ignore the flask metal part here, then mainly it is sand. Weight of the sand actually here in a cup, only cup, not drag, only cup, because this one which pushing down, which is equal to m multiplied by g. Weight meaning mass multiplied by gravity acceleration. Mass of the sand here or the cup multiplied by gravity acceleration, which is mass equal to rho v g, and this is mass equal to rho v. Rho is the sand. First rho of the metal. Be careful. In the pressure we consider here, when we talk about bouncy force, it is always liquid. This is the liquid condition. But here when you talk about the cup, it is sand condition. So rho of the sand multiplied by g multiplied v of the cup. We need to obtain the volume of the cup. So rho vg of the cup. This one if you ignore the flask. If you would like to consider the flask, it means that the weight of the cup equal to weight of the sand plus weight of the flask. Weight of the sand, which is mcg of the sand, and weight of the flask, which is weight of the flask, mean mass of the flask multiplied by g. Mass of the flask also equal to rho of the metal that being used to manufacturing the flask multiplied by G multiplied by the volume of the flask. If you would like, it is also same. So weight density of the sand multiplied volume of the sand, which is this one. If you would like to consider flask, it is weight density of the flask multiplied by the volume of the flask. It's exactly same. But we usually ignore flask. So if you ignore flask, this is the weight of the cup as made of sand. As made of sand. So raw sand multiplied by G multiplied by VC, which is the volume of the cup. I'm telling again, volume of the cup, not volume of the drag. Drag not considered here. Only we consider volume of the cup, because this is the part that pushing down, the weight of the cup which is pushing down. Then we have liquid force, bouncy force, and we have weight of the cup. We compare which one is bigger. If weight of the cup is bigger, then okay. If weight of the sand, if the liquid force is bigger, then you need to add it clamping force. You need to add it clamping force. Right. This is the issue. Let's take an example and see. Any question before we go? Any question? Muhammad, yes.
What is the weight density of the sand?
Yeah, this is a weight density. Rho G meaning weight density. Rho G is a weight density. Weight density mean rho G, gamma. Gamma meaning rho G. This is the weight density, understand? This one. This is a weight density, okay?
Yeah, okay.
Muhammad, okay? You understand?
Yes, okay.
Weight density mean rho G. The meaning of weight density, not density, but weight density. Density meaning rho. Weight density mean rho G. Right? This is the meaning, the difference between density and weight density, right? Any question, guys? Any question? Right. Okay, let's just take an example and see how to apply this kind of information in example. Consider cylindrical shape cast. This one, the cast here, cylindrical shape cast. This is the cast. Cylindrical shape cast meaning this part is cylindrical. It means that the cast here that we use is cylindrical shape, right? This is what meaning cylindrical shape cast. Okay, consider cylindrical shape casting of 4-inch diameter. Diameter of this guy is 4-inch and 15-inch long. I mean length here 15-inch. So 15-inch and 4-inch diameter, right? Cup dimension, cup, this one. This is a cup. This is a cup. Cup dimension 30-inch, and 10-inch in deep. 10-inch in deep meaning it is 30, and 10-inch in height. The height of the cup 10-inch height, and it is like square 30-inch and 10-inch in deep or height. Will the weight of sand in a cup enough to keep mold from being separated? This is a question. هل وزن الرملة اللي موجود في الكب sand اللي موجود في الكب enough to prevent this mold from separating، يعني ان هو يتفتح؟ معنى كده ان احنا يعني in another word we need to calculate the weight of the cup and we need to calculate the bouncy force and compare, explain your answer and so on. Assume that sparrow and riser and so on. So no problem. Is given here, what's given? Weight density given. Weight density meaning rho G. Weight density of liquid material is given. In this problem, weight density of liquid material is given, and weight density of sand is given, which is rho G. Rho G of liquid given and rho G of sand are given. Okay, we need now to calculate in a very simple way bouncy force and weight of the cup and see which one is bigger. Then when you go that, this is the first one, we start with the bouncy force. Start first with the bouncy force. Okay, guys? Bouncy force. Okay. The bouncy force here, liquid here is cylindrical shape, as you can see. Then it is cylindrical shape, 4-inch in diameter. Diameter is 4-inch and 15-inch long. This is the one 15-inch long, right? Then when you calculate the bouncy force, how to calculate the bouncy force? Rho GH. This is pressure. Weight density multiplied by height to get the pressure. We need to calculate the pressure. Two things we need to calculate. Pressure as a parting line and the area as a parting line. Pressure as a parting line, rho GH. Rho GH. Rho metal. G is gravity acceleration. Actually, rho G given. In a problem, he gave me the weight density of the liquid given. Then this one is given, which is this 500 multiplied by H. H here, actually, where is the H? H here, when you said H here, which is the height of Sparrow. The H here, to obtain the pressure at the parting line, we said that the height of Sparrow, this is applying pressure at the parting line. So we need to obtain what is the height of Sparrow. Height of Sparrow, he told me that the cup dimension is 30 millimeter, 30 millimeter, or 30 inch, 30 inch, and 10 inch in height. 10 inch height, meaning the height of the Sparrow is 10 inch. The height of this one is 10 inch. Actually, it is 10 divided by 12 because this one is inch and you need to change to feet. Then the 12 here is only and only to change the unit from inch to feet. But we're not going to use feet at all. We're going to use millimeter and centimeter and meter. This is kind of example. Then the 12 here being used, it is 10 millimeter height or 10 inch height. The H here is 10 inch height. So we divide by 12 to make it feet. Not inch but feet, because here this is 500 pound per feet cubic feet. Then you have to this one make also feet. So this is the pressure. This is the pressure. Where is the pressure? Pressure at the parting line. You must consider that this is the pressure at the parting line. Then when you come to the bouncy force, bouncy force equal to pressure multiplied by the area at the parting line. Where is the area at the parting line? This is the area at the parting line. It is a rectangular shape. 4 diameter, then diameter is 4. This is 4 millimeter, and this one is 15 inch. So 4 inch, sorry, 4 inches is 15 inch. Then you can see that this is, let me just highlight. This is the pressure. Pressure is here, right? Multiplied by pressure multiplied by area at the parting line. So this is the area at the parting line. Area at the parting line. The area at the parting line equal to 4 multiplied by 15. 4 multiplied by 15. Why it is the 12 here? 12 here to change also to feet. Because this is 4 inch, this is a 15 inch. Because of this one we calculate as a feet. Then you here have to make it 4 divided by 12 to make it feet, and this 15 divided by 12 to make it feet. This kind of using same unit. Then multiply by area. Then area, this is the area. This is the area multiplied by the pressure at the parting line. Then you get the bouncy force. So bouncy force 173.6 pound. This is a bouncy force at the here parting line, which is a liquid force. So liquid force, now we know this is the first question or first part. Second part, we need to calculate what? The weight of the cup. We need to calculate the weight of the cup. So second question, we need to calculate the weight of the cup. So when you're calculating the weight of the cup, actually cup made of both sand and flask. Here ignoring flask. He says that ignoring flask. Flask will not consider. Then we need to calculate the weight of the sand here, or weight of the sand in the cup, or weight of the cup equal to weight of the cup equal to mg multiplied by mc, mass of the cup multiplied by g, gravity acceleration. Mg, which is a weight, m equal to rho g, then rho g, m equal to rho v, sorry, then rho gv. Rho g is the weight density. Rho g is the weight density of the sand, which is given. Weight density of the sand is given. We need just only to calculate the volume of the cup. We need to get the volume. So this one is given, already given. So we need to calculate the volume of the cup. So what is the volume of the cup? This is a question. What is the volume of the cup? He told me that the cup is 30 inch, and 10 inch. Then 30, 30, 10. Then you get the volume of the cup. But he said that this area is not sand. Half of the part here, half of the cylinder here, not sand. Because this is liquid. You have to subtract liquid from the sand here. Then we subtract half of the volume of the cylinder, half of the volume of the cylinder. This is the volume of the cylinder divided by 4 square multiplied by 15. This is the volume of the cylinder. So we subtract here half of the volume of the cylinder to get the volume of the sand. Someone told me that we need to subtract the Sparrow and open riser and so on. The science finds that this is not significant actually. No need actually to subtract these values. Only subtract half of the part is located here. So no need actually. It just ignores the other opening, which is this kind of sparrow riser and so on. Then you get, this is the net volume. This is the net volume of the sand. This is the volume of the sand. So this is the volume of the sand, as you can see here. So this is the volume of the sand. Right, so the volume of the sand already obtained. Then rho g, we know that it is given, it is 100. This is the volume of the sand. Then you get is the weight of the cup. So weight of the cup is known now. This is the weight of the cup. The weight of the cup is given now, known, calculated, 515 pound. We need to know what is the bouncy force already obtained in the last step here. It is 173. So bouncy force 173. Weight of the cup is 500 something, then meaning that okay, because the weight of the cup bigger than the bouncy force, meaning fine, meaning this one okay. Otherwise, if what? If the bouncy force, otherwise, if the bouncy force bigger than the weight of the cup, what you can do? Then you need to do clamping, and the clamping is the difference between the bouncy force and weight of the cup, as we just described earlier. Any question? Any question? Is it clear? I think very simple. I think this is very simple, right? Another problem, the disc shape casting 300 millimeter diameter, 100 millimeter in height. Disc shape. We casting disc shape. This is a disc shape. This is a part here. This is a part actually. This is a part that would like to shape. It is disc shape. Disc shape, as you can see here. The disc shape, we're going to cast a disc shape 300 millimeter diameter, 300 millimeter diameter, and 100 millimeter heights. This 100 millimeter, 300 millimeter diameter need to be cast, and the casting process. The parting line, listen to me carefully, guys. The parting line at the top of the disc. This is the parting line. This is the parting line. Top of the disc means that we put all disc just below the parting line, nothing above. All disc will be low. Someone said, why we didn't cut twice and put up and down? No need. This one very simple. This one very simple. You can just cast here. Actually, if you can avoid having a cavity up and down, it will be better, because having cavity up and down will be more complicated than this one. Easier to put in one place. This one very simple. You can put here. But sometimes shape is complicated, very complicated, and you must have up and down. So in this one very simple, then you put down and parting line here at the top of the part. The parting line at the top of the disc height as shown in the figure below, as you can see here. Density of the multi-material here given, density of the multi-material 8,000 kilogram per cubic meter. Calculate. The force here, dimension is given. He didn't give me the dimension of the cup, but here this is 300. So this is 300. This one 700 mean it is 700. This is the cup dimension. The cup dimension is given here. This one 100, which is here. Diameter of this one is given 300. So diameter of this one 300. This one is 100, and this one 300. This one 700. This is the dimension given here. We need to know what is the bouncy force, and we need to also calculate the force, cup force, if this is the sand. This is the density of the sand. So density of sand given, and also density of the multi-material given. It is exactly the same. We need to calculate the bouncy force. We need to calculate the cup weight, and then we compare both of them and see whether this one can, the cup weight can prevent this one from opening or not. Then let's go one by one. Start one with the bouncy force. This is a liquid. This is a liquid, right? So bouncy force equal to what? Bouncy force equal to rho GHA. Rho GHA. Rho GH, which is the pressure at the parting line, multiplied by area at the parting line. This is the area at the parting line. You agree? This is the area at the parting line. So rho is rho given. G is 9.8. Because here give me rho, not weight density, but density. 8,000 is given. G is a 9.81. H here is the height of the sparrow. H is the height of the sparrow. Go back. This is the H. This is the H. This is the H needed, which is the height of the sparrow, which is a 300 millimeter. So 300 millimeter, you divide to make it meter, because this is meter, this is meter. The 300 millimeter you divide by 1,000 to make it meter, multiplied by the area. Area of the parting line, circle area. which is pi d squared divided by 1000 to make it millimeter, to make it meter, sorry. So rho g h a, this is a bouncy force. This is a bouncy force. When you come to the cup, when you come here, clamping force, we need to calculate the clamping if needed. Then to need to calculate the clamping, we need to calculate the weight of the cup. Weight of the cup equal to mg. mg, m cup divided by g. m cup equal to rho g vc. Actually here, no subtraction, because no liquid here in the cup. If you talk about the cup, we need to calculate the weight of the cup. There are no any liquid in the cup here, so we're not going to subtract anything as we did previously. There are no any liquids, right? Then we know we're not going to subtract anything. Then we need to get the volume. Volume is 700, 700 multiplied 300. This is the volume of the sand. Then rho GV, rho GV, rho G is because it is mg, mass multiplied by g. Mass meaning rho v, rho v, rho v multiplied by g. Rho is the sand. Rho of sand is given, and g we know, and vc we can calculate. Then rho vg. Then rho is given, and 9.81 multiplied by, this is the volume of the sand, but you divide by 1000 to make it meter. Then you get weight of the cup. This is the weight of the cup. This is a bouncy force. You compare the bouncy force and the weight of the cup, you find that the weight of the cup bigger than the bouncy force, meaning okay. No need for clamping. Clamping force here is 0. We don't have, or we don't need to have clamping force. This is example, right? It's very simple actually. Core bouncy force. Actually, time is finished and I have to stop here. Next time I'm going to talk about the core bouncy force, right? I'm going to stop recording now.